Hi, this is the second video in the series on exponential models. The first video was introducing the exponential models and also worked through a series of examples trying to demonstrate some of the different types of questions you can ask about an exponential model. In this discussion here, I'm going to talk about half-life models, and a little bit about doubling time models. These are reformulations of the exponential model, which make it easier for us to work with them outside of the world of mathematics. The third video in the series will be concerned with the Newton cooling process and also some financial models. Half-life problems arise not only with radioactivity, but also when we're talking about the decomposition process, say related to a chemical compound that decomposes, and where the rate of decomposition is proportional to the amount remaining at any time. Here we have a different story. A pesticide sprayed on tomatoes decomposes into a harmless substance at a rate proportional to the amount remaining. That's the clue that we've got an exponential decay here. 1 week after the fields are sprayed, it is found that the initial amount of pesticide has decayed to 1/2 its original amount. So that's a half-life information right there. The Department of Agriculture considers that a safe level of the pesticide at harvest is 0.25 kilograms per hectare. The fields are sprayed 10 days before harvest time. Find the amount of pesticide that may be used on each hectare of land if there is to be a safe level at harvest time. Before solving it, I will note that I do expect that some of you probably would claim that the only safe level of pesticide at harvest time is 0 kilograms per hectare. But it's still important for you to understand how this calculation is made, because even those that you disagree with are going to be using a method something like this, and you should know the workings of the minds of the people you disagree with. Okay, solution. In this problem, we should work with time set in days and then reconcile all of the times to days. The half-life for this problem is lambda equals 7 days. The P0 is the amount that we're trying to find. It's the amount applied. And P of t, the amount of time later, is then given by a formula. P of t is P of 0, 1/2 raised to the power t over 7. So that's t over the half-life. In this problem, we're given both that t is 10 and P of 10 is 0.25 kilograms per hectare. This comes from the sentence that the fields are sprayed 10 days before harvest time. So we have 10 days after the pesticide is applied. We have 10 days for it to break down, and at that point there's 0.25 kilograms per hectare. We want to know P0. Well, we have 1/2 to the 10 over 7. That is because we know that t is 10, and so we can calculate a value for 1/2 to the 10 over 7, and it's just 0.3715. To get P0, the amount that we need should have at the beginning, we would take P10, so that's the P of t over here, and divide it by the 1/2 to the t over 7. So we divide it by 0.3715. P of 10 is 0.25, and so the initial amount is 0.673 grams per hectare. So that's the maximum amount that we can spray 10 days before harvest if we're going to end up with 0.25 grams per hectare at harvest. Doubling models are really just like half-life models, only they're used for processes of showing growth, not decline or decay. So we might have a population where we know that the population is doubling every 11 years. And so we would have a doubling time, a beta of 11 years. We may have an investment that's doubling every 7 years. So beta, the doubling time, will be 7 years. Again, we can think of our model as having its time changed to time divided by doubling time. So we have the number of doubling units that our time represents, and for each of those we multiply by 2. So A of t, the amount of time t, is A02 to the t over beta, over the doubling time. And we could do a series of problems with doubling times, and in fact we did do that in the first video. There was one doubling time example there. Now, in fact, these other ways of formulating exponential models are not really fundamentally different from our general model using E. If A of t is A of 0 e to the kt, then that same A of t can be written as A of 0 r with k replaced with k over log r times t. So we can change the base to any other r that's positive as long as we change k by dividing it by the logarithm of r. And this means that this same function can be represented as an exponential function with any base that's positive, but simply by changing the constant in front of the variable t here. So for half-life models, we just change A of t to 1/2 kt over log 1/2. To make it a doubling time model, we take A02 to the kt over log 2. And so we can do this shifting into different bases, and by choosing these bases appropriately, we can actually use half-life models for decay processes, doubling time for growth processes, and this makes it much easier for everybody to understand what's going on in the model. Now, to summarize this particular video, half-life and doubling time models are very common, and they are reformulations of the general exponential model. Half-life and doubling time models allow us to specify the k in a way that makes sense to the world outside of mathematics, and every exponential model can be rewritten as a half-life or a doubling time model. And so they really are not, these are not special cases, but they are more appropriate in particular applications.